Hello, and welcome to video lesson number 1 on normal stress. Our learning objectives for this lesson are for you to be able to define normal stress and state the units for it, and to calculate normal stress in axially loaded bars. For this lesson, you should also be reading Beer and Johnston, section 1.2a. Now, to define normal stress, let's imagine we have an axially loaded bar that carries a force P and has a cross-sectional area of A. We would define the normal stress here as sigma equals P over A. That's a very important equation. So in the equation, sigma is the stress, P is the axial force, and A is the cross-sectional area. The units of sigma, denoted by the brackets here, are F over L squared, force per length squared, or force per area. And that can take on several different units that we'll use from time to time. It could show up in pounds per square inch, or PSI. It could show up in kilopounds per square inch, or KSI. It could show up in newtons per meter squared, or pascals. And one really useful conversion to remember through the whole course is that if you get units in newtons per millimeter squared, the stress would end up being megapascals. We have a sign convention for normal stress that would say sigma is positive for tension and negative for compression. Let's consider a calculation example. Right here. So for the composite bar, we would like to determine the normal stresses in each section. So you'll see that I've got a stepped shaft. I've got a larger cross-sectional area because I've got a 2-inch diameter rod between A and B. I've got a 1-inch diameter rod between B and C, and I'm loading the rod with 5 kips at B and 10 kips at C. That means at point A, I have a 15 kilopound support reaction. So in order to calculate the stress in section AB and in section BC, I need to figure out what the axial forces are. Now for bar AB, what I would do is I would pass a section through bar AB. I would ignore the bottom part of the bar, and I would realize that the internal force has to balance the 15 kips of support reaction. Hence, bar AB is in 15 kips of tension, so we are recording that as a positive number. Now for bar BC, what I would need to do is I would need to take a look at one side or the other of the cut section. If I was to take a look at the bottom part, I would see that I only have 10 kips pulling down. Therefore, I have to have 10 kips pulling up in bar BC. So the internal force in bar BC would be 10 kilopounds of tension. Alternately, if I took a look at the top part of the cut, I would have 15 kips pulling at A, 5 kips pushing at B, and I would still have 10 kips of tension in bar BC. Now, to calculate the stresses in each bar, I would use the formula sigma equals P over A. So sigma AB equals PAB over AAB. So that would be 15 kips. And I would use the formula at the cross-sectional area equal to pi over 4 times the diameter squared. So for section AB, that is pi over 4 times 2 squared, or 4.77 KSI. For section BC, same thing. the stress is equal to PBC over ABC. PBC is 10 kips, and the cross-sectional area is pi over 4 times d squared. So we would have a stress of 12.73 KSI in section BC. And that concludes video lesson number 1.